This is Edexcel Further Pure 1 Calculus, further methods in calculus, and in particular the use of Taylor series method for series solutions of differential equations. And to be able to follow this beyond following on from the previous two videos, you're going to need to know about solving differential equations and what they mean. If you haven't studied that yet, you need to go back and study differential equations and solving them, probably second order at least. We can find approximate solutions to differential equations using a Taylor series. If we have a differential equation where the first derivative is some function of x and y, and we're given initial conditions of x equals x naught and y equals y naught, then we can develop a series solution as below. So the nomenclature here is different, but it is pretty much the same. We're saying that a that we're taking away from x each time is actually x naught. The first term is y naught, the initial condition, and this here is saying it's the first derivative of y with respect to x evaluated at x0. So that's like the first derivative at x naught, which is just our replacement for a in the series. The key difference here is that y naught is the value of y when at x naught. And so you can see it follows on with the same method all the way down. We have x minus x naught all squared over 2 factorial, x minus x naught all cubed over 3 factorial. And we've got the first derivative, second derivative, and third derivative all evaluated at our x naught value. So you can see the close relationship, it's just written slightly differently. We can do the same with higher order differential equations, but we're going to need more initial conditions because we need enough information to be able to isolate each individual derivative and be able to evaluate at x naught. In this example, we have a second order differential equation, so the number of boundary conditions that we need has grown by 1. We've got a value of x, we've got a value of y, but we've also at the same time got a value of dy by dx. And we're also asked to go up to and include the term in x cubed, which means we need to evaluate the third derivative as well. Now we're told that x naught is 0. So that actually reduces our Taylor-like series into becoming more like a Maclaurin series. So we've got our initial condition and we don't have to subtract anything from x because x naught is 0. So you can see it looks much more like a Maclaurin series. And the key thing is that we need to evaluate y naught, dy by dx with the value x equals naught, and the second derivative and the third derivative. So let's go ahead and do that. We're given 3 of the 5 values that we need. So we then need to find out the second and third derivative values when x equals naught. To find the second derivative value, d2y by dx squared, we'll just substitute the given boundary conditions back into our equation A. So y equals 1, and we've got our d2y by dx squared at x equals 0. dy by dx equals 2, and we've got to square it. Y equals 1, and that all equals 0. Collecting the numbers together and evaluating yields the result d2y by dx squared when x equals 0 is equal to -3. We still need to find d3y by dx cubed, and the only way we're going to be able to do that is to differentiate our original equation. So the first term is a product rule requirement. So we differentiate the first term, y, so that becomes dy by dx, and we leave the second term unchanged. Then we leave the first term unchanged and differentiate the second term. Well, d2y by dx squared differentiates to d3y by dx cubed. The second term can be thought of as a product rule problem again, because we've got dy by dx multiplied by dy by dx. So we can leave dy by dx alone, but differentiate the other term, which is d2y by dx squared, and then we swap them over, and so we end up with 2 of the same derivative. And the derivative of y is just dy by dx. Now we've got values for everything in here apart from d3y by dx cubed, and there's no need to sort of collect terms together at this particular stage, because we're just going to be substituting numbers in anyway. So dy by dx we're given as 2, d2y by dx squared we've worked out as -3. We have our third derivative there. We take our 2 down, dy by dx we've been given as 2, d2y by dx squared we've worked out as -3, dy by dx we're given as 2. Collecting terms and moving all the numbers over to the right hand side yields this result. d3y by dx cubed when x equals 0 is going to be 20. So we now have all the values that we need to substitute into our Taylor series. So y0 is 1, dy by dx at x equals 0 is 2, d2y by dx squared at x equals 0 is -3, and d3y by dx cubed at x equals 0 was 20. And we have a 2 factorial and a 3 factorial here. Simplifying those numbers, we end up with 1 plus 2x minus 3 over 2 x squared plus 10 over 3 x cubed. And that's our approximate series solution for y for this differential equation. That was Edexcel Further Pure 1, Calculus, Further Methods in Calculus, the use of the Taylor series method for series solutions of differential equations. Next up, Leibniz's theorem.